For this lab, we're going to go through and do a little bit of background information to learn about light, either to refresh your memory from a previous lecture course, or just in case you haven't gotten to this part in your current lecture course. So when we look at white light is actually the combination of all the colors of the rainbow. So we can manipulate light to spread it out so that we can see those different colors in different locations in space, just like in the figure that I'm showing right here. So we have a flashlight shining through a very narrow slit that is then hitting a prism, and we can see that the light that comes out of the prism has been spread out into the rainbow from red through purple. So when we do this, we're spreading the light out in terms of its wavelength. So different types of lights have different wavelength, and by wavelength we mean the actual physical distance between, say, two crests here to here, or two troughs here to here. Either one is fine. Now, all light travels at the same speed, so if one type of light has a longer wavelength, we're going to get fewer crests coming by in the same amount of time as a type of light that has a shorter wavelength. So the amount of light coming through, the amount of crests coming through in a certain amount of time is referred to as the frequency. So we can use either wavelength or frequency to describe different types of light. And all of this is because every single type of light travels at the exact same speed, known as the speed of light. So I generally refer to wavelengths when I'm talking about different types of light. Other people prefer frequency. It usually depends on the type of light that they refer to. But I wanted to make sure you're aware of both of these because you'll hear both of them come up. So for example, if you ever listen to over-the-air TV or over-the-air radio, so not internet streaming or anything like that, or satellite, well, even satellite, but regular over-the-air AM, FM, when you're changing your radio frequency, you're actually changing and picking out, your radio is picking out different frequencies or wavelengths of light that correspond to the radio station that you want to hear. So your radio box, your antenna collects that light, it is actual light even though you can't see it, and then your radio box converts that to sound so that you can hear it. So sound is different than light. So the electromagnetic spectrum includes the full range of types of light, and I'll zoom in on this figure here in a little bit so that we can see things a little bit better. But the longest wavelength light is radio, and then there's an intermediate part here called microwaves. That is actually the part that is created in your microwave to cook your food. Then we move into the infrared. This little narrow rainbow here is visible. This is the only types of light that our eyes are capable of seeing. Other animals can see outside of this range, but humans can only see within that range. And then every once in a while there'll be a human that can see slightly outside that normal range, but that's because everyone's different and we expect some differences. Then we move into ultraviolet light, X-rays. These are just like the X-rays you might get if you break a bone or if they want to check to see if you have cavities in your teeth. And then the shortest types of light are gamma rays. So if we zoom in to this a little bit, and we'll lose some of the radio information, we can see a few different examples here. So we've got numbers that correspond to the wavelength. So again, if it's 10 to a negative number, we learned this from our math notation lab. That means that number is smaller than 1. So these things are many times smaller than 1 meter. So 10 to the negative 12 or 10 to the 12 corresponds to a trillion. So that means gamma rays is somewhere in the 1 trillionth of a meter range. So imagine taking 1 meter and dividing it up into a trillion little pieces. One of those pieces is the wavelength of gamma rays. Whereas the visible range is pretty close to 1 millionth. So you take 1 meter, divide it up into a million little equal pieces, and one of those pieces corresponds to the wavelength of light that our eyes can see. And again, because the smaller they are, the more you'll get coming by in a specific amount of time, The frequency down here is much higher. So 10 to, this is a positive number, so we know this is a very large number. So we'll have lots of those crests of the waves coming by in a second, for example, of gamma rays than we would of visible light. So 10 to the 10, that's 10 billion. So these waves are moving very, very fast, and our eyes are able to detect that in this range again. And then lastly, we know that the energy associated with a type of light is based on the frequency or wavelength. So the higher the frequency, the more energy that light carries. This is why radio waves that go around us at all times are not damaging to our body. So those radio waves could be the radio waves from our radio signals. They could be the radio waves from our Wi-Fi, from our wireless phones. Most any communication device we use is using radio waves. And those waves are so big, roughly football field size, depending on exactly which type you're talking about, and so low energy that they don't interact with our human body much. Infrared, that carries enough energy to warm you up. So when you're outside on a sunny day, a good portion of the reason why you're getting warm is from the energy from the light that's hitting you. And that's a lot of infrared and visible as well. But a flashlight doesn't necessarily warm you up quite the same as being outside on a warm day. Ultraviolet, these are more energetic. So ultraviolet light, if you have too much of it or too much of certain types, can be damaging to your skin. This is why we wear sunscreen when we go outside. So if you take a look at the sunscreen bottles, they usually say something like UVA or UVB protectant. The UV stands for ultraviolet, and the A and the B correspond to different types of ultraviolet light, so specific wavelengths. X-rays, again, in very small doses are okay, but if you're continually exposed to X-rays, that would probably cause cancer and other issues. But that's why when you go and get X-rays, if you've ever had this done, they cover whatever part of your body that's not being X-rayed in a lead blanket, and that's to protect that part of the body. So they're only exposing the part of the body that needs to be exposed. And then gamma rays are actually used in medical procedures as well. So if you want to learn more, you can Google gamma knife procedures. So because gamma rays are so small, they can use them to do more precision operations, oftentimes in places where you wouldn't necessarily want to put a knife or a scalpel. So trying to excise a tumor in your brain or somewhere in your body where they aren't comfortable actually cutting you fully open and using a blade, they can essentially take multiple beams of gamma rays that all intersect in the problem point where they want to kill that tissue. But they are very energetic, so you need to be very careful. And not necessarily every hospital has this capability. So this is all about the electromagnetic spectrum. And the reason we're talking about the electromagnetic spectrum today is because we are going to, in this particular activity, going to examine some spectra of galaxies. So we can learn about what makes up an object by looking at the spectrum. We can also figure out generally how hot it is, or how hot different parts of it are. We can figure out what it's made out of. And in some cases, which will be the end result in part 2 of this particular activity, we can use it to figure out how fast something's moving. So first, I wanted to briefly talk about how we can figure out what it's made out of. So if you heat up a very dense object, this could be like the stovetop on your electric stove. If you turn that burner on, that burner will eventually turn very red, so that way you know that it's hot. That color red is based on the temperature of its burner, and so that happens and gives us a continuous spectrum. So if you were able to spread the light out that's coming from your stovetop, you would see a curve that looks something like this. Now, if you have just a low density cloud of gas, and you can go through, and there's lots of YouTube videos on this, and you'll probably learn more about this in lecture, you can give enough energy to gas so that it gives off light as well. But when you do that, you only get the light that corresponds to the specific elements in the periodic table or molecules that are in that cloud of gas. So that means when we take a look at that picture of the light being spread out like a rainbow, we don't see the full rainbow. We actually only see certain bars of color. And each of those bars of color corresponds to a specific element or molecule. So if we look at the pattern that we see, we can figure out not only what elements or molecules are in that cloud of gas, but also how many of them there are on a rough sort of percentage type scale. Lastly, if you have some combination of these two, you have some really hot, dense source, and in space, maybe this is a star. And then there's a cloud of gas between that star and us. That cloud of gas could be the atmosphere of the star. I'll show you what our sun's spectrum looks like in just a minute. Or it could be just a random cloud of gas between that star and us, just floating out in space, which does happen. Then what we'll have is we'll have the full rainbow from the hot star, along with missing colors. And those missing colors correspond, again, to the elements and molecules that are in that cloud of gas. So if that cloud of gas by itself, it would be giving off that light. But because that cloud of gas is between us and some really hot source, we see that as missing light, because that cloud is actually absorbing those very particular wavelengths of light. And again, you've either learned more about this in your lecture class, or you will learn more about this in the lecture class. The thing that I want to focus on right now is that we can use the spectra to figure out what's inside of objects. Now, for each of these pictures, I have what your eyes would see, and then I also have the graph that scientists would draw, because we want to be more specific and accurate and precise with our measurements. So what we'll do is we'll use a computer to measure for every, so this is different wavelengths along the horizontal here. For every horizontal point along here, our computer will measure how much light we collected. And so that way we can turn it into a graph of intensity, or how much light versus wavelength. And so this is what you're going to see as part of this lab. You'll see graphs that look kind of like this. And so these dips that we're seeing are places where that light is being absorbed by the cloud of gas, or maybe many clouds of gas. So I mentioned that we would take a look at what our solar spectrum looks like. So this is a very detailed view. If we were to spread that light out, then this would be one very long horizontal strip, but that won't fit on your screen. So we've divided it up into different chunks. So it's kind of like once you get through the end of this orange line all the way to the end, then this is the next piece on the next line. So you can see that not only are there different black spots in here, those black spots again correspond to the dips. They're called absorption lines because the light there has been absorbed by that cloud of gas. You can see that some of them can be very skinny, some can be very wide, some are darker than others, some are lighter than others. And that's because not all of the light needs to be absorbed, and maybe some will absorb a bigger range of wavelengths than others. It all depends on the element, molecule, and how much of it there happens to be. But we use computers to essentially pattern match this. So by looking at this spectrum, putting it through a computer, we can figure out exactly what the sun is made out of, which is amazing when you think about it, that something like this is allowing us to do that. But that is exactly what scientists are capable of doing. So I mentioned earlier that in addition to figuring out what's inside of an object by looking at its spectrum, we can often figure out how fast it's moving. And in order to do this, we use something called the Doppler effect. Now, the Doppler effect is something that you've probably experienced before. If you've ever been on the highway in a car and had an emergency vehicle come up with its sirens on from behind you and pass you. So presumably you're pulling over on the side of the road if this is happening, although maybe they're coming the other direction. But when they're coming towards you, you will hear one tone from the emergency siren, and then when they move past you, it changes a little bit. And you can hear this when you've got fast cars moving near you, whether that's NASCAR or random people street racing near your house, as happens to me. But you get that sort of effect, which, apologies if that sounds horrible in this video, but hopefully you understand what I mean. So that change in pitch is due to the fact that at one point the object making the noise is coming towards you, and then eventually once it gets to you and then starts to move away, that sound changes, that pitch changes when it moves away. So I've got some sort of pictures to show this, and we'll talk about it with sound first. Trains is another example. So if everything is staying still, then everyone's going to hear the exact same pitch. And pitch, when you're talking about sound, is talking about the frequency of the sound. So again, sound waves have a wavelength and a frequency as well. They do travel at different speeds, so we have to be a little bit more careful with that as opposed to light. But the idea is transferable. So if you understand it with sound, then hopefully you can understand it with light. So if everything is moving, is staying still, or all moving at the same speed in the same direction, then we all hear the same thing. So if you ever go to a music concert, you're not going to hear different sounds or tones as someone in a different location, because you're all relatively staying still compared to the speakers and the band and that sort of thing. But if the object making the sound is moving either towards or away from you, then you will hear something slightly different. And this is basically because those waves, the sound waves, get bunched up for if the object is moving towards you. So it's emitting these sound waves equally, but if it's moving towards you, then they get bunched up in the front. And so you hear a higher pitch. So this would be like when the emergency vehicle is coming towards you. And then if it's moving away from you, if you're this person, now the sound waves are getting stretched out so that there's more time in between each of those crests, and so you hear that as a lower pitch. The same thing happens with light, except instead of hearing a different sound, we can see a different color. Now, in order for this to actually take effect, the object have to be moving pretty fast for you to see a difference in the color, but they don't have to be moving very fast in order for us to detect a difference in the color. So when police officers or baseball teams, for example, use radar guns to either measure how fast your car is moving or how fast a pitch is thrown, they're utilizing the Doppler effect with radio waves. So you can't see the radio waves, first of all, nor could you see the fact that the radio waves bouncing off your car or the ball are changing in any way. But the radar guns can detect that. So the radar guns are designed to send radio waves out to hit the object and then come back. And because the object is either moving towards or away from the radar gun, it can tell how fast it's moving because it knows what frequency and wavelength it sent out in terms of radio waves, and it's going to detect something different when it comes back. So if the object is moving towards the radar gun, it's going to detect a higher frequency or a shorter wavelength. And if it's moving away, then it can detect a lower one. And so radar guns then can tell us how fast things are moving because they can measure how much of a change there was. So this is the same way that astronomers do this. So let's imagine that we've got a spectrum that looks like this. We'll focus on just 3 bright lines. So this is what you see when you look at hydrogen gas. These are actually the 3 most common colors in the entire universe, shown up here in the top one that says stationary, because hydrogen is the most common element in the entire universe. And in fact, this one right here is the brightest. We call it H-alpha. It's a red line. That's the most common color in the entire universe. So if I were to look at hydrogen gas, spreading that light out into a spectrum here at my home or in the office in a classroom, I would see something like this. But if I put that hydrogen gas tube on a train that was moving away from me, I would see that all 3 of these lines got shifted to the red end of my spectrum. And the faster that train moves, the bigger the shift would be. Now, if I put that same gas tube on a train that was moving towards me, I would see everything shifted towards the bluer end of the spectrum. And again, the faster that train moves, the bigger the shift I would see. So those radar guns essentially are saying, okay, I know exactly what wavelength I'm sending out, and then I happen to get back something that is this different, and then it then turns that into a number to say that is a 90-mile-an-hour fastball, for example, or your car is going 5 miles over the speed limit. So the radar gun is doing all of this for you I would gather that most police officers don't know how to calculate this themselves. So the amount of that, we call this either a blue shift if it's moving towards us, or red shift if the object's moving away. The amount of that shift tells us how fast the object's moving. But there's one caveat to this, and that caveat is that we can only detect the amount of speed or motion of the object if it's moving exactly towards or away from us. And what this means is if we are looking at object 1, and object 1 is moving along this red line here, and I measure its Doppler shift, then I know exactly how fast that object is moving, because it's moving directly away from us here on Earth. But if I were to take a look at object 2 is moving along this gray arrow here. That's not moving towards us or away from us. So I actually wouldn't detect a shift at all for object 2. And then for object 3, it's kind of a combination, right? It's moving away from us, but at an angle. So what this means is my Doppler shift isn't going to tell me its true speed away from us. It's only going to be able to tell me part of its speed. So sort of, it's going to give me a minimum speed. And so every time we do this, we know that that speed could be higher than what I detect, because there could be some side-to-side motion that I'm just not capable of seeing utilizing the Doppler shift.